Imagine crafting the perfect operational amplifier circuit, expecting a pristine output, only to find a subtle yet persistent direct current shift. It is a common challenge for many designers, leaving them wondering about the hidden forces at play within their seemingly ideal components. Operational amplifier bias currents cause output error because these small, necessary direct currents, flowing into or out of the input terminals, create unwanted voltage drops across any external resistances in the signal path. These voltage drops are then amplified by the operational amplifier, resulting in an erroneous direct current offset at the circuit's output. The fundamental reason for these bias currents lies in the internal architecture of the operational amplifier, specifically the input differential amplifier stage. Transistors, whether bipolar junction transistors or field effect transistors, requiring a certain amount of current to operate correctly and ranges in their active regions. For bipolar junction transistor input stages, base currents are essential, while for field effect transistor inputs, tiny leakage currents still exist. Even in an ideal scenario where both input currents were perfectly matched, their interaction with the resistance of the external circuit would still lead to an unwanted voltage at the input. To understand and mitigate this effect, consider the resistance path from each operational amplifier input terminal to ground. For the non-inverting input, this is often straightforward. For the inverting input, however, you must calculate the Thevenin equivalent resistance seen by that terminal, combining both the input and feedback resistors. The bias current flowing through these resistances generates a voltage, and the operational amplifier amplifies this voltage just as it would any legitimate input signal. The key is to ensure that the direct current voltage drops across the effective resistances seen by both input terminals are as close to equal as possible to minimize the differential error. A practical and often overlooked design detail is the input offset current, which represents the difference between the bias currents flowing into the inverting and non-inverting inputs. While the input bias current, which is the average of the two, contributes to a common mode voltage, the input offset current is the primary culprit for uncompensated direct current errors. Precision applications frequently specify operational amplifiers with extremely low input offset currents to manage these subtle differences effectively. Utilizing a compensating resistor in series with the non-inverting input, equal to the parallel combination of the inverting input series resistor and feedback resistor, can significantly reduce the output error by balancing the voltage drops. By understanding that bias currents are inherent to the operational amplifier's internal structure and interact with external resistances to create voltage offsets, you can strategically design your circuits. This careful consideration allows you to balance the direct current paths to each input, effectively minimizing unwanted output errors and ensuring your amplifier performs closer to its theoretical potential.